does the reconstruction work? Major workout. That's right. Okay, we're ready to start, David. Okay, so now the plan is the reconstruction. So what have we done just so far in the Fourier business? What we've done so far is we've pretty much just described how the scanner did a Fourier transform of the brain. And so let's start with that. So we said our signal, our complex valued signal that we get out of the RF coil, if we draw it out in 2D, has it's a bunch of spatial frequencies. That's the K, KX, and KY. So it's all the possible combinations of, like one cycle of this, 3 cycles of this, 1 cycle of this, 4 cycles of this, etc. All the possible combinations. There'll be a data point, a complex data point. And so what did we describe what the scanner was doing? So this is a physical thing the scanner is doing, and we're saying what it's doing is like a Fourier transform. So here's our Fourier transform, and the Fourier transform says we sum across all x and y points in the image. So here's the image. So that's an xy point in the image. And then it's multiplied by this e to the minus I 2 pi. And then we can either add the exponents ky times y, or we can multiply 2e to the minus 2 pi kx x times e to the minus 2 pi ky y. So we can either multiply 2 e's, or we can just add the exponents. And then that's summed across all points in the image. So what are the parts here? So this is the signal. This is the signal. RF signal, RF coil signal, RF coil signal after. So RF coil signal after phase sensitive detection to bring us down to the rotating coordinate system, all that stuff. This is the RF coil is doing this sum here. It's adding up across, doing complex vector addition across the whole brain. This is the brain, the image, and that's a real image. It shouldn't have any complex part. And then these things are the gradient caused spin phase wraps. So those, and we said, if you turn the gradient on for 1 unit of time, you'll get, there'll be 1 ahead at the top end of the gradient. You turn on for 2 units of time, there'll be 2 ahead at the top, and then you just keep letting it go. So that does all the phase wraps. This is definitely complex. Real and imaginary part to indicate, like, which direction the vector is pointing. Now, notice here what we've put in for the equation is an exact sign, exact sines and cosines, or a vector of, so this thing is a vector of length 1, and as you change x, it's a perfect sine wave and a perfect cosine, this equation is. Now, in real life, that's not true. So this equation, this is important to keep in, this equation assumes perfect gradients. They're not perfect. So we'll see when we do the reconstruction that we use this same equation, so it's kind of asymmetrical between the Fourier transform done by the scanner and the inverse Fourier transform done to do the reconstruction. When we do the reconstruction, we use perfect sines and cosines. When the scanner does it, it uses something that's approximated by perfect sines and cosines. So this was the summary of everything Fourier up until now, that the scanner does a Fourier transform of the brane. Here's the real brane in XY, and it does it by stamping on these phase stripes and then adding them all up. It adds them up for each single point in k-space. So each single point in k-space, whatever kx and ky is a result of adding across the entire brane these phase stripes, multiplied by the actual amount of brane there. So that's the first part. So how do we do the reconstruction? So the reconstruction is exactly the same thing. It's so easy. So here's our image, because the inverse Fourier transform is basically the same thing as the forward Fourier transform. So how do we get the image in x and y? We just do the inverse Fourier transform, which is exactly the same thing as the forward one. So here's, we'll now sum across all of k-space. So this is all of k-space. And what are we summing across all of k-space? Well, our signal. So here's our signal, complex signal, at kx, ky. So these are all the points in k-space. And what are we doing with them? We're just multiplying them by sines and cosines. But the only difference is the plus. And we can write this one backwards. So sort of sometimes people write that backwards. It doesn't, multiplication commutes, but we'll write it backwards to indicate we're doing a inverse Fourier transform. And then this is for every point. So the only difference between the inverse and the forward Fourier transform is this sign right here. Otherwise, the operation is exactly the same. So the important thing here is that, use perfect cosine. And so what is the, where did this thing come from? Well, that's basically just that. So very strangely, we've arranged the scanner to do a Fourier transform of the brane, and now we've got this Fourier transform of the brane, and then all we do is just Fourier transform it again, and then we get the brane back. Now, typically, this image will be complex. And so what we always do is we take that complex image and, so here's one data point in the image. It will have some phase angle. But what we do is so here's the real and imaginary part of it. So it will have an imaginary component. And so what we do is we just calculate the amplitude of that data point, image data point. So this is, image x, y, which is a complex number. We take the amplitude of it, throw away the phase angle, and just show you the amplitude. Now, in real life, the brain doesn't have any imaginary part. And so if everything was perfect, if all the gradients were perfect, then we should always get a 0 phase angle, or it could be a minus 180 phase angle. So we should always get vectors of different lengths, but they should never rise up onto the imaginary axis. But our data is never perfect, and so there can be substantial phase errors. And so the problem with the phase error is, say the phase error was 90 degrees. If the phase error was 90 degrees, that means if we just looked at the real component, which we know it's supposed to be, we would get 0, because the real component of a phase angle equals 90 is, the real component is 0. So the image would really be completely, if we ran the data, collected data, Fourier transformed it, and then threw away the imaginary component and just showed the real component, which is what it's supposed to be. It's supposed to be a real brain. You'd end up with just a complete mess of a picture, because some parts of it would be completely black, because they would just happen to accidentally have gotten a 90-degree phase. So this is, so for this, get amp toss phase. Now you don't have to toss the phase. So the phase has some useful information in it. In particular, it tells you that there was a B0 defect, for instance. And so it's possible to save the phase. And so you can tell the scanner, I actually want the complex data, because I want to actually use the complex data. People rarely do this, but it is possible to save it. Okay, so now, how is this actually done? So I drew this out as a 2D Fourier transform, but how is it actually done in practice? It might be worth just going over this quickly. So the way it's done in practice, so if we look at, so remember, if adding exponents is the same as adding exponents equals multiply e's. So we could rewrite this one out as we sum over the k, y, kx. Let me put that up a little bit higher, because I want one under it. So we sum over the ky, kx. But here's our signal, kx, ky. And we can just separate these out. I mentioned that above. So it's plus I 2 pi x kx times e to the plus I 2 pi y ky. So that's equivalent. And then we have for every x and y point in k-space. So then what we can do is, if we sort of, if we just move this guy into here, we can see that this guy is just a 1D Fourier transform. So we could write it out again, strangely, as sum across all ky. Yeah. So let's just rewrite this guy as a 1D Fourier transform. So now we're summing across just kx of our signal, k-space signal, and times this guy plus I 2 pi x kx d kx. Done. Okay, so this is our 1D Fourier transform. And then we take the result of that and Fourier transform it. So here's the outer one. And so now we just have another, another e to the plus I 2 pi y ky dky. So what does this mean? So it just means that a 2D Fourier transform like this can be performed in the following bizarre method. So you start off with some k-space data. So here's kx, ky. So it's got a bunch of stuff in the middle. So that's our k-space. And then what we do is we just do a 1D Fourier transform of this data, like this. So just Fourier transform all the just in the x direction, and then put the data back in there. And so now what do you have? So now what you have is something that is in this direction. It's an image, but in this direction, it's still k-space. So you basically just take a line out, run a 1D Fourier transform on it, and then put the numbers back in there. And so you end up with this strange animal that's like half image, half k-space. And then you just do a Fourier transform in the other direction. So this is our 1D ft, and now we have 1D ft the other way. In the y direction. This guy is 1D ft in the x direction. And so then what do you get? Then you get a brain. So this makes a brain. So that's actually the way it's done. It's even done that way in MATLAB. It's more efficient to do it that way. So sometimes you'll see in different pulse sequences, you might end up with a weird situation like this where you just do a Fourier transform in one direction, but you've got this strange animal that has like image going this way, but it's still k-space going that way. But that's amazingly is just a very simple manipulation here. We just took these sum of exponents, turned it into multiplying two e's times each other, and then we just recognized, well, that's just a 1D Fourier transform with this 2D data. So this is 2D data, but we're just doing a 1D Fourier transform on it, and then the result we get, we just insert into the equation and do another 1D Fourier transform on it. Okay, so that was how the reconstruction is actually done. So the gradients do the make the stripes. That calculates a Fourier transform. It makes your signal a Fourier transform, and then we just get an image by just doing a Fourier transform again. And then we typically throw out the phase. So that's the reconstruction, but what we haven't talked about is all of these equations I'm putting up are sort of infinite equations. They're going across, infinite amount of image space and infinite amount of XY space. And that's clearly not what we're doing. We're only recording a finite number of data points. And so the problem is what happens when we only record a finite number of data points? And that's called a discrete Fourier transform, and that's different than this, in some respects, the simpler one that we're doing that sort of goes out to infinity. So we need to talk about the discrete Fourier transform. So it's virtually identical to the regular Fourier transform. So if we write it out for, say, reconstruction, so I'm just writing out the second equation that I had up there before. So here's the discrete Fourier transform. So it's just going to be equal to not an integral, but just a sum of a finite number of things. And we're using m and n for number of points, and small m and small n for current point. So it's going to be equal to, if we write it out like the way that it's actually done, there's a Fourier transform of our signal. It's a complex signal, again, at point nm. So, and then times our e to the plus I, 2 pi. And now instead of, so normally what we would have expected here, what our cerebellum would have expected here, would have been a kx. But instead what we have now is n times k, we have n times delta kx. So that thing, so what does that mean? That means like the fourth point in k-space times the spacing in spatial frequency of the k-space points. So this thing is basically equal to kx. It's a way of sort of stepping through, using finite steps, to step through kx, spatial frequency. So what is the difference? The difference is in the integral Fourier transform, we had spatial frequency 2, and then we also had spatial frequency 2.001, and then spatial frequency 2.002. So we have like an infinite number of spatial frequencies. In this case, we just have a discrete number of spatial frequencies. So that n is an integer, current point, integer. So that's like 1, like 1, 2, 3, 4. So it's 1, 2, 3, 4 times the spacing in k-space of the next, it's what is the spacing in spatial frequency to the next k-space point. So that's the only difference of the discrete Fourier transform equation. And so then we have another, and so this guy is, spacing in k-space. So the spacing of the next sample in k-space. So, and then since we're doing it the way that we had it at the bottom where we do two 1D Fourier transforms, here's the second Fourier transform. So that's just e to the I 2 pi m times the spacing in the y direction. So, oh, sorry, forgot one thing. There's one other difference. We're multiplying now by an actual finite number. So here's the spacing in the kx direction. So we're multiplying by that guy. It's in the exponent, and then we're also multiplying it. That's the equivalent of in the integral equation where we had dkx, sort of infinitely small sample of kx. But here we're actually multiplying by a known amount of it. Let me just draw it out there so it's really clear that it's not in the exponent. So times delta kx. Okay, and then we have to do another Fourier transform of that in the other direction, and that's just d to the I 2 pi m times delta ky, and then that whole thing times delta ky. So those are the two differences between the integral one. Here we've got an actual number, it's not an infinitely small thing, and here instead of kx we have nkx, and here instead of ky we have mky. So that's the plan. So what's the problem? Well, so the problem is a lot of different things happen when we just sample discrete points in k-space. And the first thing that happens when we do that is we get replicas. So there's two things we're doing, two things to keep in mind. So two things are, not infinite, infinitely high spatial frequency. That's one thing. But the second thing is, discrete samples. We're skipping. So, so there's two things going on, have different effects. So we're skipping some data, and then we're also not going out to infinity. Those two things have different effects. So what are those effects? So if we look at starting, so here's the space side of things, and here's the spatial frequency side of things. So we'll do 4 different cases. So the first case is the infinite case. So we have a brain here, and here's where our picture would normally go to, but now we're just sort of imagining we start off with an infinitely large brain. There's nothing else in the universe, there's just a brain, and then there's infinity of space on either side of it. That's what the Fourier transform equation says. And if we, and so what is that? If I just draw it out in 2D, what does that look like in 2D? Well, it kind of looks like, something like that. That's my approximation of a brain in 1D. Sorry, you go across the brain, it's black. Something comes up, and then it's no longer black. And what does that look like, when we do a Fourier transform of it? We can do a Fourier transform this way. It looks like, more or less like a sink. Sort of like a boxcar sort of Fourier transforms into a sink. Sort of looks more or less like, something like that. Not quite, but, that's more or less what a Fourier transform looks like of a brain. It's got a big spot in the middle, and then it sort of spreads off on the side. So if I draw that out in 2D again, what does that look like? There's like a, some data in the middle, but, it's got a lot of data in the middle, but notice we've got infinite k-space. So, k-space goes off in all directions. We would always draw that, the integral out with, from k, x equals minus infinity to kx equals infinity. So it goes out forever. If we inverse Fourier transform this, then we get back just one brain. So that's good. But now we've got to do two things. So the first thing is just to discretely sample it. So now we've got our brain. We're still assuming it's got infinite amount of space around it. But we're now just sampling our data. So what does that mean? So it means our data is still going to be a sink, but we're only going to just sample the sink like this. We'll still go off forever, but we'll just have discrete samples, so skip some spatial frequencies. So it still goes off forever. So this one goes off forever. So what does that look like, in k-space? Well, it just looks like, we're not filling in all the intervening points. So, we just got samples at discrete points in k-space. We don't have infinitely fine samples. So what does that do when we do the inverse Fourier transform? So if we take discretely sampled data like that and do an inverse Fourier transform, what it does is it introduces replicas. And so what does that mean? That means there'll be another copy of the brain over here. And there'll be another one over here, and another one over here, another one over here, another one over here. So there'll be a whole array of brains. Now, you might have heard of wraparound. This is actually what wraparound is. Wraparound is basically these replicas kind of intruding into your current brain if you haven't set something right. So that's step one. So that one was discrete samples. So that's what discrete samples does, a ridge. So here's a ridge. Here's discrete samples. But now we've got another problem, which is edge. So discrete samples of k-space makes replicas. So now we're also not going up, we're not going up to an infinitely high spatial frequency because we only got a certain amount of time to collect the data. And so what does that mean? That means like, we cut off, we sample our k-space data here, but then we cut off, a hard cutoff, and stop. So we don't go out to infinitely high spatial frequencies, which we could do with a discrete Fourier transform. We could, record for all infinity, but we'll just stop. So what does that do? So what that does is that's going to cut off really fine details, so our image will have a finite amount of, I'll just write it out. So we'll have some blurring, no, high spatial frequencies. So that is another way of saying we'll have a finite voxel size. So if you zoom in on the image, it's blurring anything smaller than a voxel because you didn't collect that data. So there's no way that you could actually sort of resolve something smaller than a voxel because you just didn't collect any high spatial frequency data. But there's another thing that occurs. You get some ringing. So what happens is if you use a Fourier transform to reconstruct something that looks like this, when you do the reconstruction, typically what you'll get is something that's sort of got a little bit of a wiggle right around where there's an edge. So it'll come like this. It'll go up and down and up and down like that. Then up and down and up and up and down. So you'll get a little bit of ringing when you don't have an infinite set of spatial frequencies. So not only is it blurred, you lost high spatial frequencies, but there's this other problem. Okay, and so then the last, so this is we get blurring. So this is discrete sample. This was not to infinitely high spatial frequency. But there's another thing that could happen. What if we, and I'll talk about this a lot more next time, what if we don't sample k-space densely enough? So what if we space out our samples like this? Then we have the tragedy of wraparound. So when we do that, what will happen is it will cause the replicas to intrude like that. So, and then we'll see this, so this is not dense enough. Not dense enough sampling. And so, what happens is we get wraparound. And so amazingly, that's what determines your field of view. So what does your field of view mean? Field of view means like how far can we go out without running into another copy? That's really what the field of view is. And so what controls the field of view is how densely you sample spatial frequencies. That's adjustable on the scanner. You can sort of effectively, they don't label it that, but that's actually what's going on. It's like, are you sampling like spatial is your delta kx? Your delta kx basically controls the field of view. So that little thing up there, for better or for worse, controls field of view. FOV. That's actually what controls FOV. How densely are you sampling k-space? And if you spread out your samples, it's just like everything in Fourier land. You spread out the samples here, then they shrink on this side. So if you want to push the replicas out, you have to sample more densely in k-space. And so that, just when you see that, it's just like, whoa, boy, that's just, it's just k-space land. It's just the way things happen in k-space. But this is what we actually do now. So we started off with almost all the first, parts talking about infinite Fourier transforms, which are actually, infinity sounds difficult, but it's actually easier. The equations are kind of simpler. But now we've got to deal with a discrete number of samples, and not only a discrete number of samples, but a discrete number of samples that don't go all the way out. So we're skipping some k-space points, and then we're completely not collecting any really high spatial frequency k-space points. So two things, not infinitely high spatial frequencies, and then also we're skipping in discrete steps. So let's just try in the last minute or two to get an idea of how come you get replicas. So for better or for worse, we'll try to get an intuitive feel for that from talking about sampling, our sampling function. So our sampling function is, we've got a continuous thing, but we're not sampling it continuously. We're just sort of sampling at a point, an infinitely small point. So if we start off, this is the space side, and this is the sampled spatial frequency data side. So this is like the two k-space domains. So here's our brain. Our brain is, imagine a brain, a rectangular brain. So if we Fourier transform that, what we get is our sinc function like that. More or less what our k-space looks like. So now we're going to multiply this guy by our sampling function. And so what is our sampling function? So our sampling function is just a whole pile of spikes. So our sampling function says, ignore this, just pay attention to the data at this point. And so if there's no spike there, the answer is 0. So here's a whole pile of spikes, etc. So if we multiply that, that's going to, equals. So multiply equals our sampled data. So here's our sampled data, and it's going to be, here's our sinc function, but we've only sampled it. So there'll be like a data point there, data point there, data point there, data point there. So we just multiplied it by all those spikes, and so that we just have discrete samples of our thing with 0 in between. Okay, so that's our data, sampled data. So can we use the idea about, convolve in one side is equal to multiply in the other side? So turns out you can do a Fourier transform of this thing. And what does it look like? Well, it looks like some spaced out spikes. And pretty much, it's sort of a very Fourier transform type thing. So if you scrunch these spikes in, these guys get further apart. So the Fourier transform of a bunch of spikes with 0 in between is another bunch of spikes that are sort of inversely related. And so what happens if we convolve on this side? So remember the rules for convolution, it's like a blurring operation, but if you've got a spike, what it does is it just makes a copy of the thing you're convolving it with. So if we convolve that guy, then it just equals replicas. So it just takes that one. Here's the center one, and then there'll be another one down here. So those are our replicas. Etc. And so that's one way of thinking. Where do the replicas come from? It sort of has to do with the fact that we're discretely sampling the data. And so when you multiply a continuous function that has like a zillion numbers in between here by the sampling function, the end result is you have to sort of convolve your image with the Fourier transform of this guy, so that these guys are all Fourier transform pairs of each other, going back and forth. So, this is the bottom line. So we get replicas. Replicas when we take sampled data like this and inverse Fourier transform it, that aren't there if we have infinitely fine sampling. You can sort of think of like if you scrunch these guys together and more and more and more, these will eventually go out further and further until there's only one. So that's the original case when we're sampling infinitely finely. So we're sort of into the standard Fourier transform lore of how to think about like what's actually going on in the scanner. What is actually field of view? So what I'll do next time is I'll go over very concrete, more helpful examples of how you control the field of view. How do you change voxel size? So there's several things going on. How do you change the voxel size and how do you change the field of view? Those are two different things. You can do those independently. So just more practical things about how you actually sort of modify this on the scanner and how is it represented on the scanner. But this is just a standard introduction to, with all the details left out of, what happens when we discretely sample data. So you do this all the time if you discretely sample audio data and do a discrete Fourier transform on it. That's all practical Fourier transforms are like this. They're obviously not doing infinitely high spatial frequencies. Okay, so let's end the recording here, David, and I'll take some questions.